All right, welcome back to our section 10.4, which is titled Random Variables and Probability Models. This is the second video in which we are going to cover binomial probability models. We're going to start with this video by doing example 4, which is going to introduce us to this idea of binomial probabilities. We're going to talk about some probabilities that we've basically touched on before involving rolling a die, and then we're going to relate it to our new concept of binomial probabilities. So, example 4 says, imagine you roll a die 4 times, find the probability that we're going to roll all threes, no threes, and then exactly 2 threes. So just related to what we did in our last video in the beginning of this section, I have let x equal the number of threes that we're going to roll. That's our random variable. So the reason why we call this random variable is because it can take on multiple or different values. It's not like solving for a variable in algebra class where you get your final answer of x equals 3. Our random variable here takes on different values. You could have, if you roll a die 4 times, you could have 0 threes, you could have 1 3, 2 3, 3 threes, or 4 threes. So there's different values that this random variable could take on. So the first one we're going to find is the probability that our random variable x equals 4. In other words, that we roll 4 threes. So what we have here is 1/6 to the 4th, because each time you roll the die is independent of the next, and the probability of rolling 1 3 is 1/6. So you're going to do that 4 times. The probability of rolling all threes is 1/6 to the 4th, or 0.00077. Now obviously this would be the same probability as rolling all of any type of number, but we're just focused on a random variable being rolling a 3. So the next one that it asks us about is the probability of rolling no threes. So we're looking for the probability that our random variable x, or the number of threes that we roll, is equal to 0. So if the probability of rolling a 3 is 1/6, the probability of not rolling a 3 is 5/6. And we're going to do that 4 times in a row. So 5/6 to the 4th would be 0.48225. Okay, you can give this as a percentage, you can give it as a decimal, the way that we've been doing in our probability problems so far. The next problem gets a little bit more interesting because it says we're going to roll exactly 2 threes. Well, I just have an example here. If you roll a die 4 times, let's just say that we get our threes in the first 2 rolls. I don't know why that's not showing up. So we get a 3, and then since it says exactly 2 threes, those are the only 2 threes that we can get. That means that the next one would not be a 3, and the last one would not be a 3. Well, that's only one way that you could roll 2 threes. You could also have not 3, and then 3, and then 3. So there's different ways that that can happen. We'll get to that in a second. But this probability would be 1/6 times 1/6 times 5/6 times 5/6, using the probabilities that we use in A and B. But that's, again, that's just one scenario. So that probability is going to be 4 choose 2 times that 1/6 squared that we have right here, times the 5/6 squared that we have right here. So where is this 4 choose 2 coming from? Well, the 4 choose 2 is us saying we know there are other ways that we could roll 2 threes other than in just the first 2 rolls. So what we're trying to find out here is, in 4 rolls, how many ways can we roll 2 threes? So that 4 choose 2 covers that part of the probability. So we have 4 choose 2, which, if you remember from your Pythagorean, or excuse me, your Pascal's triangle, if we're talking about our 4th roll, the Pascal's triangle, 4 choose 0 is the 1, 4 choose 1 is 4, and 4 choose 2 is that 6 right there. So 4 choose 2 is 6. I don't care if you guys just type it in your calculator. You could type this all in at once, but this value here ends up being 6 times 1/6 squared times 5/6 squared. Our probability ends up being 0.116. So what we have here before I move on, what we have here is the build of our binomial probability. We are going to be finding the number of ways that we can have a certain number of successes and a certain number of trials. Here our number of trials was 4. We were rolling the die 4 times. Okay. The number of successes was 2. We were looking for 2 3s. The probability of success was 1/6. And we took 1/6 the number of successes that we wanted to have, which is 2. The probability of failing here was 5/6. And by failing, we mean not rolling a 3. And we knew that that would have to happen 2 times as well, because we had a total of 4 trials. Right, this should look somewhat familiar. This is related to the binomial expansion that we've done in the past, where we had to expand a plus b to the n, and we would use a number from Pascal's triangle as a multiplier, and then a to the n, and then that would go down by 1 each term, and then b to the 0, and that would go up each term. It's the same build in this formula. So then let's piece together how we find any binomial probability. It says the random variable that the random variable that counts the number of 3s we get when we roll a die repeatedly has a binomial probability distribution. In a binomial probability distribution, each trial has 2 possible outcomes. We consider one outcome a success and the other a failure. The trials are independent of one another. For example, the problem that we just did, we were rolling a die. When you roll a die over and over again, those rolls are independent. Okay, the probability doesn't change. The die doesn't know what it just rolled. It doesn't care. The probability of success on each trial is the same. And we denote the probability of success as P and the probability of failure as Q. Note that 1 minus P is Q, or another way to say that is P plus Q would be 1, because they're complements. You either succeed or you fail, because we said you only have 2 outcomes. So here we have the formula for finding the probability of a binomial distribution, binomial probability. That the probability of x, so I'm looking at this right here, the probability of x equaling a certain number of successes, k, would be n choose k, which remember we said that this notation here means the same thing as n choose k. And we're just using k instead of r like we did when we did combinations earlier. And then you take your probability of success to the number of successes that you expect to have or that you want to have, and the probability of failing to the number of failures that you have. And n minus k will give you the number of failures, because n is your total number of trials. If you subtract the number of successes, that'll give you the number of failures that you're going to have. All right, so I wrote that formula again here on our next page. Probability of x equaling k is n choose k. Okay, again, that's just n choose k. If you want to write it like that instead, that's fine. And we have this example here. It says, suppose Michael makes 90% of his free throws. Okay, so we're going to say that the probability of him succeeding then is 90%. We're going to say making a free throw is a success. He's going to shoot 20 free throws. So 20 represents the number of trials. So I'm just going to put this here. The number of trials is 20. N equals 20. The probability of success is 0.9, 90%, and the probability of failure is 0.1 then, because he can either make the free throw or miss the free throw. Those are your 2 outcomes. The probability that Michael makes all 20 of his free throws, well, really that's just going to be 0.9 to the 20th, or 0.2158. Okay, we don't really need to use the formula for that, because it would be 20 choose 20, which is just 1, and then p to the 20th, which is what I'm sorry, 0.9 to the 20th, which is what we have, and then q to the 0, because he's not going to fail at all. Well, q to the 0 is just 1, so we don't need to worry about that. So it's just 0.9 to the 20th. The next one says exactly 18. Well, that would be the probability that x equals 18. Okay, x is um, the number of free throws that he makes in 20 shots. So now we have a chance to use our formula here. So we have 20 choose 18. We have 20 choose 18, and then 0.9 probability of success taken to the number of successes, which is 18. And 0.1, that's the probability of failing, taken to the number of failures. If he makes 18, he's going to miss 2. And that probability is 0.28518. Now I'm going to show you how to do this on your calculator in 2 different ways. Okay, obviously you could type this in, and I have this first here. You could type that in using combinations and exponents just like it looks, and that's going to give you the 0.28518. But notice this next one that I have here, this binomial PDF. Okay, your calculator has a special distribution menu for calculating different distributions, and like we said, this is called a binomial distribution. So we're going to do this on our calculator using the binomial PDF. I'm going to show you how to get to that. Right, so on your calculator, you want to find the distribution menu. That is right above the vars button, the variables button. So you're going to go second, and then the variables button, and that takes you to, if you see above it says DISTR for distribution. We want the binomial PDF. So if you scroll, I think going up is a little bit faster. If you scroll up to A, I think even on the old calculators it's also A. If you scroll up to binomial PDF, we don't want CDF, not yet. We only want PDF, and I'll explain what CDF is in a minute. So we want binomial PDF, we're going to hit enter. Now, on the newer calculators, it makes it pretty easy because it gives you the template to put in the number of trials. We had 20 trials. Okay, Michael's going to shoot 20 free throws. He's going to make 90% of them, so his probability of success is 0.9. We are in example B here looking for the fact that he makes 18 shots. So we are looking for exactly 18. All right, now if you have an older calculator, when you go to binomial PDF, it's going to give you an empty parentheses. What you want to do is type in exactly what you see here. Basically, you are typing in, I'm going to write it on the smartboard here, binom PDF, and then in the parentheses you want to put N, and then comma, and then P, and then K. Or I guess, I think your calculator calls it X, but it's the number of successes. I'll put K because that's what we had in our notes earlier, was the number of successes was K. That's how you type it in if you have an older calculator. Okay, so it looks just like we have up here. And when you hit enter, you get the same exact answer that we did before. Your calculator calculates that binomial PDF for you. Okay, now I guess I will point this out right away. The reason why we use the PDF here, the P is that we want to use the PDF when we are finding an exact number of successes. So the fact that it said exactly 18 meant that we wanted to use binomial PDF. The PDF stands for probability distribution function. We'll use the CDF when we want to add probabilities together, or the cumulative probabilities. That's what the C stands for. We'll get to that one in a second here. So the next problem says, what's the probability that Michael makes at least 18? Well, there's a couple of different ways you could do this. Probably with what we have here, the easiest way might just be to find the probability of 18, 19, and 20. We've already found 18. We would just need to find, oh, actually, we've already found 20 as well. That was in the first problem. We actually really only need to find the probability of 19, so that's the only calculation that I've shown here. So this 0.2158 came from the first thing that we got, and the 0.2518 came from the second answer that we got. And then the only other thing that I calculated was the probability of Michael making 19 out of his free throws. And that ends up being 0.2702, if I can read that tiny writing there. So if we add those three things together, we get 0.6769. But I'm going to show you another way to do this. Using our calculator, we can use the fact that what we don't want to find here is the probability that he makes 0 through 17. Okay, because we were asked for the probability that he makes at least 18, and we've used this concept before. To find the probability probability of at least something, you can take 1 minus the probability of what you don't want. So you're probably thinking, why would I want to find the probability of 0, 1, 2, all the way through 17, add those together when I only had to add 3 of them together here? Well, it's because your calculator's CDF function will calculate that 0 through 17. The binomial CDF function calculates anything from 0 successes up to the number of successes that you put in. So if I put 17 in, it's calculating 0 through 17 successes and adding all of those together. So that's a pretty hefty calculation. So if we type that into our calculator, we get the same exact answer. All right, but you got to make sure you put in 17, not 18, because 17 would find up through 17, which is what we don't want. And then when we subtract that from 1, that's going to find 18, 19, 20. Let me just throw that on the calculator here real quick. Second distribution, we're going to go get the binomial CDF this time, which is right here. How many trials? Still 20. Michael still shoots at a 90% percentage. Now we're looking for 17, but you have to understand, when you type in 17 right here, because you have the CDF function typed in, this is going to calculate all the probabilities from 0 through 17 and add them together. So if I hit enter here, you get 0.323, and you could have just typed in 1 minus that right away. But now I'm going to go 1 minus second answer to give me our final answer of 0.677, which is what we got up above. So those are a few examples of the binomial distribution. What we're going to do is finish the rest of these notes, which will continue this example with Michael in our next video.